Excellent. So good morning and welcome to this session, which is Measuring Adversary Costs to Exploit Commercial Software, the government bootstrap non-profit CITL, and the speakers are Mudge and Sarah Zatko. For reference, this is South Seas GH, and we've got a few brief notes. One is to stop by the business hall located in Bayside AB during the day, and for the welcome reception from 5:30 till 7 tonight. The Black Hat Arsenal is on the Palm Foyer on level 3. And join us for the Pony Awards in the Mandalay Bay BCD at 6:30 this evening. And just as a quick reminder, can you put your cell phones on vibrate, etc.? I know that's a lot more fun anyway. So just so we don't interrupt the conversation. So without further ado, Sarah and Mudge Zatko.
Thank you. Okay. Appreciate it very much. I'm Mudge, this is Sarah. I do want to do a really quick shout out because two people aren't able to watch the presentation right now because they're watching our infant child in the speaker room. It was one of the challenges of the couple presenting together. But she has the former White House Director of Transnational Threat, Paul Kurtz, and Commander John Kaltwasser of the U.S. Navy watching her, so I think she's in pretty good hands right now. Why don't we start off?
Great.
Oops.
So,
can you not see it there?
Yeah. All right. So, as they said, we are a 501c3 focused on assessing software risk. Our way of focusing on software risk is the cost to an adversary to newly exploit a piece of software. And this is preliminary data, just a peek behind the scenes. So the problem is obvious to everyone here probably. That we've been trying to get people to care about security for years, and whenever somebody says, okay, I care, what am I supposed to do? We're pretty vague about the next step. We tell them which browser we think they should use, but we don't necessarily have a lot of real data to back that up. And just in general, consumers don't have much to go on when they actually decide to give a shit and try to do better, and that's a problem. So what has the industry done so far to try and address this? There's been several different avenues. First off is certifications and evaluations, which they'll be pretty upfront about the fact that they aren't really about security. And most of these are focused on processes and procedures, not on the actual product that comes out of those procedures. So they don't always work for what we're looking at. There's industry and marketing labels, but those are frequently vague or misleading. And if somebody has two pieces of software with the same sticker on them, they don't know how to judge between those. The company just has to do the minimum to get to that sticker, and then they're done. Source code review definitely has its place, but it's not getting the whole picture. And it has the wrong incentive structure for helping consumers, because usually the people doing source code review, either it's internal or it's the vendor paying to have their code reviewed or a large company. But in either case, there's NDAs involved and the general public never sees the results of that. Also frequently, there's no obligation to actually fix the things that are found in source code review. It can be sort of academic sometimes, you know, that, okay, we did this, but we're busy and we need to release. And then finally legislation, which is usually well-meaning, but frequently focuses on making it illegal to look at a problem rather than trying to fix the problem, and that's a terrible way to solve anything.
So with that in mind, I wanted to dive directly into data kind of early on. I'll give you a heads up. We're going to take kind of a 30,000 foot, and then we're going to dive down to microscopic, and we're going to kind of pop back up to 30,000 feet a few different times. So this might be a little bit of a bumpy ride, but I wanted to show you the depth and the breadth of the processes and the actual data that we're pulling out. So if we're able to quantify the different security features and create a continuum, what does it look like for each of these operating systems? So this is Linux. This is Linux Ubuntu with the first 10,000 applications. And the histogram here is ordered where the lower scores are on the far left, and of course the higher scores are on the far right. They're bins of 5 points each, 100 being the maximum score there. And you can see that we've called out the 5th, 50th, and 95th percentiles. If we line up underneath it, a relative hardening line that is mapped to the above histogram. And we start to plot some of the individual applications. And we're going to show little yellow triangles up top. Since we have the 10,000 apps here, which is largely the base install and a few of the more common applications here, just to kind of show you comparatively where things live, we can just dive into the data and pull out anything that we've already evaluated and have measurements on. So if we pull out two browsers on Linux, Chrome and Firefox, we see that not too bad. One of them's almost at the 95th percentile. That's relatively, not many people made it up that far. Firefox isn't too far behind, but if you start looking at the difference between the 95th percentile and the 50th percentile, we're starting to go towards the softer targets pretty quickly. And what happens on Linux if we do this sort of measurement for the Office suites that are available? Well, we start seeing OpenOffice, LibreOffice, and I called out Thunderbird there because we just happened to be looking through and saw that one as well for the mail client. And you start realizing the relative level of effort that an adversary has to go through to newly exploit. And all of a sudden, you start to realize why client-side attacks that are exploiting the applications running locally to compromise the system and control execution are so rewarding and frequently valuable to the adversary. So that's a high-level view of Linux with a few extra third parties. I'm going to go into precisely how we make up these scores and what the different moving parts are under the scene. But let's go over and look at the OSX histogram. And in this case, we have not just the base OSX, which was about, I can't remember, 10,000 or 12,000 total binaries. And those are the executables and all the libraries, because of course the libraries make up part of the attack surface. Sarah will talk to that a little bit later. But we also went out and grabbed about 20,000 other binaries from all sorts of third-party vendors. So what happens when we start to look at the relative strengths and weaknesses of different applications on this continuum? A little different story. Here are your most popular browsers on OSX. Chrome on the far right, Safari still below the 50th percentile there, and Firefox having a little bit of a problem here. One of the things that we were very pleasantly surprised about, not that it's a good thing, but we kind of looked at it and said, oh, that makes sense, is for those who have access to the underground markets for 0 days or trading or some of the bug bounties, or if you're selling things into the intelligence communities, I don't care which country. I do care which country, but for this example, it doesn't matter which country. The price tag for the exploits on these very nicely map up to the hardening line here. In fact, it's been working so well that a couple of folks that had early access to our data that were helping us vet some of this came back and said, I'm not sure I should tell you this, but we've been able to do exploit arbitrage for certain people buying 0 days, because we just look at what they're looking for, and then we look at your charts to figure out what the lowest hanging fruit is, the softest target, and we realize it's overvalued for the amount of level or effort that we'll have to do to exploit it, and we go after that, and we make more money. I said, hadn't really intended that, but I guess that does confirm that what we're doing is a little accurate. So here are the Office suites on OSX. We see Microsoft Office, OpenOffice, and OSX's versions, Keynote, etc., lobbed on there. We're always interested in a chart like this as to what the outlayers are. What's the measures of kurtosis sort of tell us about how long of a tail you have and who lives there. And for that example here, I'm going to point out two of the kind of critical pieces of software on your system, the software updaters themselves, because they are responsible for not only taking information and communicating across the network in one way, shape, or form, but also they're the ones that are installing your very security patches designed to protect your system. So we looked at and just pulled out of the large histogram of the 38,000 some odd binaries here, Apple's software updater and Microsoft's. Guess which ones ended up on which side of the spectrum? I was a little surprised. We went in because, of course, this is largely preliminary data, and when I see something that's so predominant, that's installed with every version of Office on OSX, that scores so lowly, I'm like, I must have, there must be a bug in my code. I must be extracting the wrong features. Somehow the measurement's going. And we went in and looked at it, and sure enough, it's a 32-bit binary with no address space layout randomization, no stack guards, no source code fortification, et cetera, et cetera, et cetera. And yeah, it's a really soft target. Now I went and talked to some folks on our technical advisory board, and I said, does this make sense? Are you seeing this? And one of them said, well, yeah, actually there's a spate of compromises going through OS X right now, and the one thing they all have in common is they're all running the Microsoft Office suite. So I don't have proof for sure, but if I were to go and look for that exploit, I think I know the first thing that I'd go after. Now, the next slide is a look at Windows 10. I will preface it with this is not complete, and we don't have all of the features for the data points that we are pulling out, and it is just the core installation. So there's only one third-party package, the Anaconda Big Data Analytics package, but everything else is just the core Microsoft install. So this is kind of comparable to what we were looking at on Linux. Now, this looks a little different. This is actually pretty darn impressive, because this is a level of consistency in the build process, in the build quality, in the security constraints, in the complexity, in the application armoring that Microsoft seems to be doing on their own operating system that wasn't evident in what they were doing for applications on OS X that they're selling. But this level of consistency is pretty impressive. We'll go more into detail on a few of the things that are hanging at the bottom left there on the weaker side a little bit further on. But next we're going to talk to you about what sort of data makes up those scores and what sort of breadth and depth we have and why we feel that that is appropriate.
Okay, so for figuring out how to present the data that we're looking at, we are drawing inspiration from a lot of existing labels from other industries. And so for each of the types of data we collect, I'm going to talk about what labels are comparable. Is it this one?
Right.
Okay, good. So, for example, the static analysis features, which are the contents of the software, the stuff that you get without having to, do fuzzing or dynamic analysis. This is like the nutritional facts for the software. It's the telling you what's in it and is it junk food. And the nutritional label is really a marvel of how to inform consumers, because how to figure out what you should be eating is a pretty technically complex task that everyone's been trained to. Then for the dynamic analysis, exploitability, disruptability, and algorithmic complexity, where that's comparable to like the crash test ratings that you see in a Monroney sticker when you go to buy a new car, or the EPA miles per gallon. It's stuff that they get either from running the car into a wall or until its tank is empty, or by modeling what it's going to do based on what similar cars got for their miles per gallon. And then finally, the safety continuum is very similar to Energy Guide, where you're putting the cost of ownership for this product on a scale with similar products.
So this is a breakdown of what's inside the Nutritional Labeling and Education Act, if you will, the nutrition label. And I like I just broke the microphone up here. No big deal.
Okay, I got it.
Destructo hands engage. One of the things that Sarah pointed out was this tells you the makeup of what's inside the binary, but it doesn't tell you, that it's good or bad for your particular diet. And I really like that analogy, because what we want to do here is extract the salient features that are relevant to different types of security, hardening, soft, complexity versus simplicity, et cetera, that then allow you to make an informed choice. But we're not going to tell you which choice to make. If I use the nutritional label analogy, an anorexic and a diabetic have very different dietary restrictions, but they can't follow their doctor's or nutritionists' recommendations unless they can see what the heck's in the food that they're putting into their mouth. And that's what we want to do with our static analysis component. So what we're using on the back end for the features you can largely be broken down into three separate areas. There's complexity measures, and complexity measures range from something as simple to the text size, code size, if you will, of the actual binary towards more complex like branch prediction or branch complexity, all the way up through, you know, racking and stacking the different stack adjusts inside of it, which give you some inference about functions and about how much they're manipulating or what they're doing inside, through cyclomatic complexity, et cetera, et cetera. The other section is application armoring. And application armoring is broken down into, you know, 3 sections. What does the compiler do? And there's a bunch of things that modern compilers can actually do that are equivalent to the safety features in a car. They're your airbags, your anti-lock brakes, your, you know, seatbelt and restraint systems. And you can find that in the compilers for stack guards, control flow integrity, code pointer integrity, et cetera. You see that in the linkers, where the linkers are saying whether or not, you know, this thing is able to be re-randomized and loaded in different areas, whether the linker has moved different sections in the binary, such as not to be overridable, where there is sensitive information in it. And then, of course, you know, there are instructions that are put in the binary to the loader at runtime. What should it map different segments? Is it executable? Is it not executable? Is it shared? Is it consistently, you know, kept in memory, et cetera? And then the third area is about developer hygiene. And this is built up of about 500 different functions across POSIX and ANSI that have historically been difficult to use correctly and have been the root cause of many of the security vulnerabilities that we look at. We break them down into the following categories. IC, which, you know, if you remember the poison sticker that you put underneath the detergents under your sink and everything, these are just a few functions, but you can't use them safely, ever. Git S, classic example. You see that in commercial code, you should just go run screaming. They don't know what they're doing, at least from a security perspective. The bad functions, the ones that are historically very difficult to use correctly, the unbounded stir copies, memory copies, et cetera. The risky functions, which are better than the bad ones, they bound it, but we still see people do things differently or incorrectly. Is it null terminated? Is it not null terminated? And more recently, there are a few functions that have been introduced which are actually strong. They're hard to use incorrectly. The stir-L copies, stir-L cats. And it's nice to see those in there, but it's disconcerting if you see the good one right next to a bad one in the same, you know, function or in the same code. There's a consistency issue here. All in all, there are several hundred features like this that we're pulling out, and they make up the majority of our static analysis. Which leads us to the Monroney sticker and the dynamic crash testing. The crash testing is important because, you know, it's nice to see that something is really, really weak and looks like a very soft target, but it's better to actually know that this thing crashes under pathological input. Presently, we're using AFL as our primary fuzzing engine on the back end. It's a wonderful fuzzer. We're not married to it. You can essentially drop in anything that gets really good coverage and allows you to go deep into the code. Look at any of this stuff from Brumley on the Cyber Grand Challenge, et cetera, et cetera. The goal is you just need to be doing the dynamic components. But what we do out of it is we look for 3 classes, 3 categories of response from the application. And that's the exploitability, the disruptability, and the algorithmic complexity. And it's important that we call these out because we as security practitioners oftentimes really functionally fixate on the exploitability. Was it exploitable? But as a consumer, let's assume you are in charge of an offshore oil rig sort of setup. If you ask that person, what's more important, whether the system is exploited or disrupted, they're almost always going to say the disruptability is what bothers them. If the system is compromised and they're using it for a where server or they're surfing IRC, but it isn't impeding the continuity of operations of that drill, so be it. They prefer it not be exploited. But nonetheless, if it's disrupted, that drill bit stops, everything solidifies, and that oil rig is offline for 12 months at least in order to get it back. Go ask somebody in a bank that same question, and they'll say the exploitability, the integrity of the data. Because if they start propagating incorrect, numerical things further out, it becomes more and more difficult to roll back and get back to ground truth. And then there's a different class of organization, the Googles, the Facebooks, the LinkedIns, et cetera, that are really concerned about algorithmic complexity. And it's not a hot topic yet, but it likely will be. Because what this means is these organizations are so distributed and they have such massive bandwidth. They're usually relatively impervious to distributed denial of service, which is good because their uptime is what drives them. What they are vulnerable to are denial of service that require very low bandwidth, but have an algorithmic worst case scenario on the back end that can take things out irrespective of how well distributed they are. So we use a modified version that we hope to be releasing shortly of AFL that measures the size of the input and the runtime of each of the test cases, and we can start to graph out algorithmic complexity. Is it growing logarithmically, linearly, exponentially? The latter two could be problematic for this. But that's what you see with the little squares on the far right that say A, because that's signifying that these results were actually from these real, billion executions with X amount of coverage and the results from running that particular application.
So if it doesn't say A there, what does it say? It says E for estimated. Because, as I mentioned before, when the EPA does miles per gallon, they don't run every single car until it's on fumes. They do enough that they can model, and then they don't have to do it for everything because it's an expensive operation for them. And similarly, fuzzing is expensive. It requires test harnesses and a lot of extra work for each target. Whereas once you build up a mathematical model, math is cheap. So we'll fuzz a statistically significant portion of the software, and then for the rest, we can model how it's going to do in dynamic analysis based on what we saw for the static features. And this is great for a few reasons. One, it cuts out a really expensive part of our process, and it gives us an asymmetric advantage over attackers in that they still have to fuzz because they need to find the specific location of a vulnerability in order to exploit it. We don't need to do that. We need to know what classes of vulnerabilities are there with some percentage accuracy, but then our work is done. So from a assessing risk perspective, we don't need to know where the exploit is.
So you saw on those safety continuums, the histograms, how useful it can be just to see largely static information on understanding the risk. Before we go on, this is really an icing on the cake if we can pull this off, which all of our indicators on the back end are showing that this is working for us. Because this means that we can, through linear regression of those 300 features that we're using that are security related, and the statistically significant actual crash testing, feed that into Bayesian analysis, and we can do free crash testing without having to do 10,000 hours worth of real-time fuzzing or creating the harnesses. And for the situations that are erroneous, we feed them back in, and that's the beauty of Bayes, is it essentially readjusts. So before we go in, now we're going to start looking at a subset, and we're going to do kind of different levels of views. And the subset is going to focus more on the binary extraction, the static extraction, because we're going to be releasing a lot more of the dynamic runtime results at the beginning of 2017. And we're just going to be choosing these two subsections from our data sets, and those two subsections are focused on the application armoring and the function hygiene.
Okay, so this is one of our automatically generated reports for Google Chrome on OS X. To make these, we got to spend lots of quality time with LaTeX or LaTeX. I usually read it rather than say it, so I can't remember which one people prefer. But the first page of every report is always first a table reminding us how the scores were calculated, because as we tweak these, we want to be able to look back at old reports and remember how those numbers were arrived at. And then a summary of any anomalies for that file. There weren't for this, but for some there's unusual flags or strange initial permissions for the text segment or what have you.
No.
And then we have a table of the file, code, and data segment sizes for the main application, the average library, and then the total libraries. The interesting bit in this table is that the main application's code segment is just 601 bytes. So the Google Chrome application is just a stub, and all of the real operations are happening in the libraries, which we were a little surprised to realize that's how browsers seem to be operating these days. And then we have a summary of how many libraries there were, what their average score was, and then minimum score. And the library count is how many libraries does the application link against directly, but then also what libraries do those use, and so on and so forth. So when it's all said and done, Google Chrome is requiring 176 libraries. So it's not a small amount of code. And that can all be part of the attack surface, so we have to look at all of it. Moving on to the second page, the main report. On the first column, we've got the main application at the top, and then all the libraries listed. This goes on for several pages. Clearly, that's not 170 lines. And then after that, the columns are whether it's 32 or 64-bit, what the score was, and then the two categories of columns after that are application armoring and then function hygiene, which are just a subset of our static analysis features, but they're the ones we're highlighting in this talk.
I'm doing my best Vanna White because I do realize it's a bit of an eye chart here. I apologize for the folks on the other side of the room.
Well, you got them earlier.
Yeah.
Okay. And then that was a more detailed look at the data. Taking a step back, here's a very coarse-grained view of how to compare the three most popular browsers on OS X. So we've got Chrome, Safari, and Firefox. And here, as I said, it's a coarse view. We're just looking at 4 application armoring features: ASLR, non-executable heap, stack guards, and fortified source. So each of those 4 things is worth 25 out of a total 100 points. If all of your files for the browser have, say, ASLR, that gets you 25 points. So nobody got 100, but Chrome was the only one that was pretty consistent in its use of ASLR and heap protection, so it did the best overall. Safari had everything, but not consistently, so it ended up in the middle. And then Firefox was missing ASLR entirely, which was a pretty big surprise to us and actually to some people internally there.
Yeah, this particular image was in Kim Zetter's article, and it was really interesting and enlightening to watch some of the Firefox developers go like, hey, what's up with that? Why aren't you showing ASLR? We've had that since 2012, and then, or whatever the date was. And then other Firefox developers started to say, yeah, but on Linux in the following environments, we don't use it, and we don't use it here. And then, well, if it's on OS X, because they have Safari there, so that's not on Linux. And they said, yeah, we haven't had that because anything that's compatible with 10.6, just you're out of luck. And they hadn't really realized that. And that is a significant safety harness that is absent. John Kaltwasser, our commander there, does a lot of design for capture the flags. And he was just telling us in the back, he was on School of Root, if some of you folks remember them from DEF CON, or involved there. He said, yeah, for the designing of capture the flags, in order to make some of the targets weaker, we just turn some of those features off just like this. The good news is that they're going to be enabling that apparently in the build that's coming out in September or October. The bad news is, right now, if you're using it, well, you can see it. And before I go on to the next slide, the data sets that we have are really what we're kind of creating here, both the binary analysis and the dynamic runtime analysis. And we're going to be licensing those off in various fashions as befit to a nonprofit. We're following the Consumer Reports model. And these are different ways of looking into it. We're going to be releasing various curated reports. Some will be at a high level like this. Some will be at the histogram sort of level for the continuum. And then going into the next part is, what happens when you really start to dive into the data? How rich is it? And what can you start pulling out on specific features? So many people are familiar with source code fortification. If you -D fortify source on GCC, LLVM similar. And what it does, for those not familiar, is there are about presently 72 functions that are really difficult to do correctly. And people have historically just abused these or used them incorrectly. And what the compiler does is the compiler looks at each of the 72 instances that it sees as a viable target. And in Linux, we saw 2 million total opportunities that the compiler saw. So looking at this as a platform, Linux, what can we learn about Linux and source code fortification? And if it could do heuristics to say, I see what the developer was trying to do, I can do this more safely, it will replace it with a stronger bounded version. Good. If it can't figure out what's going on, it will not touch it because it doesn't want to accidentally break the code. The way you read this chart is each one of the dots is a file, and on the y-axis is the number of instances of those 72 functions that existed in the binary. So if we see this dot over here, that's about 10,000 opportunities to replace a weak function with a stronger version. But unfortunately, the x-axis tells us that it was able to do that less than 10% of the time. looking at this as a whole, we see that about 33% of the time, 1/3 of the time, they're able to replace 95 to 100% of the functions they see, and some with significant numbers. I will call out that System D was off the chart on this side with, I think, 43,000 memcopy instances, and it was 0.7%.
Not memcopies, I think they were p-reads.
Oh, p-reads, sorry. That were unable to be, the compiler said, I don't want to break it. But while it gets 1/3 of these correct, as you can see on the far right, the other 2/3 are pretty much evenly distributed. All right, that tells us something about the Linux environment at present. What does it look like for OS X, which also has this opportunity? So rather than 2 million opportunities for replacing the functions, we had 7 million opportunities. And we see a slightly different story. We see much more of a cluster on the far side where the compiler, the developer's doing the right thing. They say, please, where you see a risky function, replace it. But the compiler says, I saw lots of risky functions. I didn't feel comfortable replacing any of them. And that's a little bit of feedback that we'd really like the developer to have that they don't. And maybe now they do. The most significant fortification that was at the 95 to 100% range only had 121 instances of functions. So that led us to believe that source code fortification is slightly less mature maybe on OS X. What would happen if we look through our data sets from the binaries on a different sort of slice on the same thing to compare? So this will be function by function. And this is Linux. So the way you read this chart is the number of functions, so in this case about 38 functions out of the 72 that are of the fortifiable type that it looks for. 38 were almost never able to be touched. These were the p-reads, the memcopies, a whole bunch of pointer arithmetics. 15 functions, your classic stir copies, etc., were able to be almost entirely replaced with their stronger area or their stronger replacement. And of course, 28 out of the 72 functions never got touched. As far as we can tell, they're largely academic, and the situation where the compiler would be able to say, I know what you're doing, I can do that safer, would be so rare as to, we didn't find it in the 7 million opportunities. Let's look at OS X. Unfortunately, it confirms our estimation. This time there were 52 functions out of the 72 that were never able to be touched, and this was off of 7 million opportunities. And we can see that a significant amount were only fortifiable very infrequently.
Only one ends up being in the 95 range. Nothing was 100% fortified. So it's just much less mature, at least based on the results.
We will be releasing down the road some information that we're gleaning about the overall ABI and the characteristics per operating system. I should point out, it is unfair to compare an application, binary, or library on one operating system to that of a different. You need to keep these evaluations for what we're showing right now within the same OS. So for a comparative view, you look at an OS X browser against an OS X browser. You look at a Windows browser against a Windows browser. We will start to explain the overall cases that the kernel operates on and the kernel offers and the environments offer. And Windows seems to offer many more opportunities to engage application armoring. But presently, please don't try and say like, oh, well, this one was low over here. How does that compare to me on Windows? You have to look within the same environment. So we talked about a bunch of different levels. I told you we'd be going up and down at the stack here. And we've looked at the continuum of an environment. We've looked at particular call-outs of application armoring at a high level, at a low level. What can we tell about the organizations, since we're looking at all this software, and you can kind of group them as to what their strengths and weaknesses are?
Well, and because a lot of these sorts of things we're looking at aren't news to people, that ASLR is interesting or that stack guards are good to have. But people usually look for these things in a piecemeal manner rather than being systematic across a whole environment. And so then when you look at it that way, interesting patterns emerge.
And wait till the next talk for all the deep dive on the measures of complexity, which we're not really looking at as our exemplars here today.
So, for example, if we look at Google Chrome versus Microsoft Excel on OS X, you can learn interesting things about what Google versus Microsoft are doing right or missing. Each of them has something they do well, and each of them has a blind spot. First, looking at the development and build environments. The application armoring columns are the part that really reflects the build environment and settings and development environment, because that's where you're having the latest and greatest compiler and telling it to do all the right things. And Google Chrome does that. They even went out of their way to figure out how to enable non-executable heap flag for 64-bit binaries. They were, out of the 30,000 plus binaries that we looked at, they were the only ones that had it. So, kudos to them. On the other hand, Microsoft Excel had a 32-bit binary that was missing some flags that were default for almost all 32-bit binaries. And what that tells us is that they were likely operating on a pretty old build system, or they were on a modern one where they had specifically disabled these, which is worse. So we're giving them the benefit of the doubt there. Not so great. But then on the other hand, while Google Chrome has more of those good functions that we mentioned earlier, they're almost always side by side with the bad and risky brothers. You have the stir-L copy, but you also have the stir-N copy and the stir copy all in the same binary. And what that means is that there's no consistent use of the good functions, which is sort of partially defeats the purpose. What this tells us is that the developers, some of them know what they're doing when it comes to security, and some of the code review people know what they're doing, but then a lot don't, and it's really sort of luck of the draw who wrote this code or who reviewed it. On the other hand, Microsoft Excel, when they have a good function, they don't have the bad or risky version also, because they have gotten beaten up over these functions often enough that they do it right. Their compilers have special settings that tell the developers, no, you can't check that in. You're not allowed to use stir copy anymore. Bad programmer.
For those of you familiar with coding in the Windows environment, from what we've inferred from public sources, they have a preprocessor that runs through their deprecated security risky functions, and they don't let internal people release code if those are in there until they're fixed, which is a more automated way of doing it rather than the kind of roll the dice that it appears that Google has, because they've got really good developers at Google, but the range of security knowledge does vary based upon developer and based upon the reviewer that you draw out of the lottery.
I'll briefly talk about one of my other pet peeves. This is because programmers graduate without having been educated on secure programming. It's not a focus of most computer security programs. But anyways, moving on.
Mm-hmm. So back to the big picture. We were having a lot of fun looking at essentially these three charts. And I don't want people to take the wrong thing away. We're picking on Microsoft there in an environment that's not a Microsoft platform. It's OS X. It's not terribly surprising to me that that's not their main focus. And if you recall from the bottom histogram, it really looks like Windows 10 in general, although this will flesh out as we add in more third-party products and as we start to do more of the features, you'll see more of a distribution across there. But that's a really impressive level of consistency for a security and software development lifecycle, at least so far. But the question here, when we step back and look at all three of these, is who's living in the bottom all the time? Because, I wanted to do this effort way back at the Loft. And in fact, some of what ultimately ended up being the inspiration for companies like Veracode, and which was Slint and some different areas that they've then taken much further, were kind of the impetus here. And I couldn't pull it off back in the Loft days because I wanted a binary analysis that would give you a traffic light, red light, green light, yellow light, just letting you know if it was a piece of crap or whether or not this looked pretty good before you went and chose it. And everything was red light, and there weren't any options. I'm on the Omni browser. Great. What else am I going to use? The other browser is non-existent. It hasn't been developed yet. That didn't work. But now, as you can see, you've got choices. And you've got choices for just about anything. So if it doesn't matter to you, if you care, if the feature set of the software is equal in your eyes, choose the one that imposes more work to the adversary without causing any cost to you. Okay. So back over to what's on the bottom side. because we can do this now. It was one set of applications that made up the very bottom, and this was disconcerting because it was also an application suite that we were using on our systems, and I thought they were fine. The interesting aspect was that a source code analysis wouldn't have actually revealed this, and here's how we first found it. Next slide, please. This is Anaconda, which is a big data analytics tool set. We'll tell you a little bit more about its background. Go ahead. We were looking at, back up one.
Sorry.
Thank you. We were looking at ASLR measurements, and at this point we were building it out on Linux. And the way you read this chart is it's fixed addresses for the symbols, fixed addresses for function pointers. Throughout it, you want 0, 0. This means that the loader and the linker say, like, you can move anything around. ASLR can be introduced by the kernel. It's good. People won't have predictable places to jump to. And as you move further to the right and further top, this is problematic. So what were the outliers? Oof. They were all from this Anaconda package. And we had seen this on OS X. And we saw this on our early stuff on Windows 10 as well. So what is Anaconda? It's a roll-up of a whole bunch of open source applications. Many of you here are familiar with like Kali, Backtrack, or whatever. It's really convenient because it's difficult to go out and curate all of those yourself and get them to link in the configuration settings to work correctly. It's got some DARPA backing, and it's Python and R and NumPy and matplotlib and OpenSSL and libxml and all the stuff you need to do big data analytics. Their list of customers on their site is impressive. It is a veritable who's who of big banks, of government, of you name it. And next slide. They were always in the bottom scores, which was disconcerting because I have OpenSSL and I have libcurl and libxml installed in different places from other packages, and they weren't in the bottom. So what the heck was going on? Across those three operating systems that we're highlighting for the exemplars today, 90% of the time, they didn't even have the modern-day relocate read-only with bind now on Linux. No stack guards in the builds. OS X missing everything from fortification, ASLR, et cetera, et cetera. Windows, this would be structured execution handlers. Thank you for the typographical correction there, Microsoft PowerPoint. And we said, oh my God, this is right back to if I want to make a trivial capture the flag binary, this is what I do in order to make it more exploitable. So we didn't get it off of OS X, although we saw this happening. We couldn't figure out precisely what was happening. When we looked at Linux, of course, it's nice because they've got an info section in the binary, and that started to reveal what we later confirmed with Windows, is that GCC compiler they're using is a 2008 one on a 2005 Red Hat Linux. So they're going out and grabbing all of this software, recompiling it for you, and then giving you a package, which is nice because it's all together. You don't have to do that, but you've lost almost a decade worth of security improvements and features to make an application more resistant to exploitation and abuse.
And without looking at the binary, you wouldn't know that it wasn't the same thing that you'd get if you had gone to all those separate locations and downloaded their packages.
Mm-hmm.
So,
go ahead.
Before we just wrap up, I'm going to go through some various things to correct misconceptions about what we're doing and make sure everyone's on the same page as us. As I said earlier, these are preliminary results to familiarize everyone with our goals and tactics and techniques, but the real data releases are going to happen end of this year, early next year. And this approach is based on binaries only, partially for reasons we just outlined with Anaconda, and then partially because having source code means having to cooperate in some way with the vendors we're evaluating, have NDAs, all that jazz, and it doesn't set up the sort of incentive structure we want to have. This is not pass-fail or gold star. It's meant to be quantified and comparable between products. And looking at overall vulnerability trends and classes rather than specific instances. This talk focused on static analysis, but the dynamic analysis and other types of data will be forthcoming next year probably, as will analysis of Internet of Things devices. We are a 501c3, which means that we are a nonprofit charity, but we have non-exclusive right to use and practice this IP, and we are looking forward to partnering with various different industries that are starved for data. Industries like insurance really needs actuarial data.
Yep.
Or
and the insurance organizations are very interested in this.
Also, security industries need data to back up recommendations or to,
right. I mean, I was talking to Chris Weisopel, an old colleague of mine at the Loft over at Veracode, and he got it right off the bat. He's like, this is very complementary to their business model because they're going to tell people precisely what they're doing or what they need to do. They are the nutritionist or the dietitian or the doctor, and this is the nutritional labels going in on it. Real quickly, as an interjection, there's a lot of confusion because, of course, I coined the term Cyber UL in regards to this. The UL is doing something different. They are a for-profit organization now. I hope their stuff works well. It is widely different than what we were doing. We are modeled almost exclusively off of Consumers Union and Consumer Reports. So if you're wondering how we're going to be releasing data or who will get access to it and what fair way, just look at Consumer Reports, and that's probably the way we're going.
We'll have to have this be coin operated in some way so that it's sustainable long term. And their model seems to work since they've been around for a while. And then finally, what we're not doing. We're not looking at configuration, vendor history, interpreted scripts, corporate policies, privacy, things like that. There's other groups that do look at these things. And if you go to some security consultancy for advice, they can help you take our data and all that other data together to come up with a unified view. It's not that we think those things are unimportant. It's just that other people are already doing those, and we want to focus on the data that's not out there yet.
So I'll wrap up. This is our timeline. By the end of 2016, you're going to see a bunch of curated data releases for us with some write-ups, think Consumer Report style. And we're releasing more of the specific details about the static measurement technologies. We've given you a high-level overview here. 2017 is going to be the large-scale access to the different back-end resources, and hopefully with enough of the exemplars that you saw here, people can slice and dice it in ways that matter more to them. Obviously, this works, especially the complexity measurements, work on any piece of binary, period. Firmware, embedded system. We're going to do this on cars. We're going to do this on real-time operating systems, you name it, because we should be able to have comparable or comparisons within those. And then middle of 2017 is when we start to dump the massive fuzzing results that comprise the statistically significant sampling and start to release the predictive ones and show you the level of confidence that the mathematical models get to. We have received some money. I want it to be very clear where the money is coming from. Ultimately, we will be Consumer Reports model driven. This is a small seedling experiment grant from DARPA. AFRL, the Air Force Research Labs, is the contractor. Ford Foundation put some funds into it, so we're working with Consumer Reports to figure out how some of these methods and methodologies can be applied in the Consumer Reports so that when you're reading their magazine, that anything that has software, or which is everything, will give you some level of ability to navigate that as well. And then, of course, the final legalese, since this is DoD funded.
You skipped AFL.
Oh, sorry. Yeah, huge shout outs to a couple of pieces of open source software. Mike Zalewski did a bang up job on AFL. That is a real nation state level sort of fuzzing environment. You're going to see more of that in the Cyber Grand Challenge backend stuff, which is just outrageous. I got to work with him a little bit at Google. He calls me out in the credits of AFL, which is just a huge honor. I don't deserve it. I did very little. And then the Capstone engine, because I originally did the disassembly myself. And of course, they have a much better approach and do a much better job on it. So that's what we're using on the back end for the disassembly. Oh, one of the questions we always get, which I'll wrap up on here, is are we afraid of the vendors? Because isn't this reverse engineering and WIPO and all of that other sort of thing? There's a big difference between reverse engineering and disassembly. And all we're doing essentially is the same level of what the computer's doing itself when it loads up the code and runs it. We don't care about the proprietary algorithms. And our lawyers, who were the first people we went to when we went on this expedition, said, "No, we're pretty sure that you're good to go. Bring it." So we look forward to engaging the folks who disagree or feel otherwise. And there's not really a website up. The website is currently .com, but all the email goes to .org. And the goal is just to give you guys a little early access. So thank you very much. Appreciate it. Hope this makes more sense.